All right. Today we would like to have another brief introduction to analog design. The content actually came from chapter 1 of the Bible, one of the Bibles from Professor Razavi, Design of Analog CMOS ICs. If you are interested, you can go back to read the chapter 1 to get better understanding and more detail. I would like to say that I think everybody here knows about digitization, 数位化. It means we would like to digitize almost everything for our new technologies. However, after digitization, why we still need such kind of analog design? Why? You can see in the past, we have analog radio, we have analog video and audio recorder, 录音带, tape, right? Everything in the past is in analog domain, but nowadays, almost everything in digital domain. So, why we still need such kind of analog design? Yeah, anyhow. From the very beginning, our voice, our image, everything, our sense. We have 5 senses, right? Your vision, your smelling, everything is in analog domain. Actually, nothing in the nature is digital. And this is the reason why we need such kind of digitalization. It means what? To convert the analog natural signal into digital one. For what? Easier and better processing. Okay, but before digitization, anything is analog. So you need to process, you need to convert, and we need such kind of analog design from analog to digital for digitization. And after that, just like what you look on the screen, all the content actually were prepared in digital domain, right? But can you enjoy such kind of digital information by yourself? If you open the file, you will see everything look like this. Even for the PowerPoint, the real content actually only has zeros and ones. Can you guys enjoy such kind of content? No, never. Okay, so for you, for the students to look at what the content is really is, we need to convert it back from digital domain to analog domain for you to enjoy. That's it. Okay? Never mind for humankind or for our pets, for your dogs, for your cats, they don't enjoy anything in digital domain. You still need to convert everything back to nature, to analog domain, for humankind and animals to enjoy. Maybe even for plants, 动植物都一样. Okay, so that is the most important issue. Even we try to digitize everything, we still need analog design. Okay, that's it. And it also hints that data converter, to convert signal from analog to digital and backward, should be the most popular design. ADC and DAC. All right, that is the top one IP for analog design. And then this is another another application, just like our mobile phone. You can see from this is for receiver. In the air, we have RF signal. But how large the signal is? I'm talking about the magnitude. Actually, that is a scale to -6 order of 10 in volt. Can you enjoy such kind of signal? No, too weak. So we need to amplify it. So we need amplifier. However, it needs to be low noise amplifier. Actually, we call it LNA. All right? Never mind. After that, we have some kind of improved version. We call it LNB and then LNC. I don't care. What is the alphabet you would like to have? Briefly, we call all of them. Never mind. LNA, LNB, LNC, LN what? All of them, in brief, they are all LNAs. Low noise amplifiers. However, if you would like to achieve such kind of low noise, you had better, for CMOS technology, you had better to use PMOS. Why? Because NMOS is much noisier than PMOS. But why? Simply because NMOS, the majority carriers is electron. And in PMOS, the majority carrier is Hall. And in next chapter, I will tell you the move. No. I would like to refresh your mind for the conduction of electrons, of holes. Then you will fully understand why PMOS is better than NMOS. I mean, for noise performance. Yeah. For speed, nothing is free. For speed, NMOS is much better than PMOS. But for noise performance, PMOS is much better than NMOS. That is, from the very beginning, you will see the word is not ideal. It's imperfect. Why? Nothing is the best. No. Okay? We always have the so-called pros and cons. 优点跟缺点. You need to accept it. In digital domain, maybe you have the best. For example, for mobile system, nowadays everybody apply ARM, right? ARM core is the best. And how about in analog domain? Nothing is the best. So in analog domain, usually you need to do something called trade-off. Yeah, 你需要妥协. Because nothing is perfect. Nothing is the best. If you would like to use something good for this issue, usually it is bad for the other issue. Okay, so you need to think, does it deserve? Right? Maybe you can change your mind to use the other architecture. Yeah, and it will be good for the other issue, but bad for this issue. Okay, that is your life. If you would like to join us, for analog IC design, you need to know how to do such kind of trade-off. Our trade-off may be a little bit dark. Okay, for the positive side, you see, you always need to do optimization. 你需要做优化. Okay, yeah, but they are talking about almost the same thing. Then I will show you the next very good example. Digital communication. Yeah. Even for digital communication, we need analog design. Why? Okay, from the very beginning. For the fundamental digital communication on board, on PCB board, actually you can transmit 1 and 0s directly from this chip to the other chip. Okay, on board. You can do it. In the past, maybe not only on board, maybe from here and for machine A to the other machine B, you can transmit digital content directly, 1 and 0s directly. Okay, but that is already out of date. Nowadays, I guess for almost more than 99% of the communications, if you would like to transmit 1 and 0s directly, only on board. Okay, off board, forget about it. Yeah, that's why. Okay, allow me to show you this, a very good example. How can you transmit the 1 and 0 from here to there? We need wires, cables, everything. Metal, nice. Okay? But again, nothing is perfect. Even you use any kind of very good metal line, it is still low C. Okay? It means what? It has parasitics. R and C and R and C. You have a lot of R and C parasitics. In such kind of structure, what kind of filter you will get? Equivalently, what kind of filter? R here, C there, R here, C there, blah, blah, blah. Low pass, right? Because the impedance for C actually is 1 over C. The higher frequency, the larger S. It means the impedance will approach 0. All the signal will be shorted. All the high frequency signal will be shorted by such kind of RC structure. That is low pass. So it's really harmful for the beloved digital signals. If you transmit 1 and 0 directly to such kind of lossy cable, what's the consequence? Because it is some kind of low pass filter. So the high frequency portion will be smoothed, will be filtered. Okay? Maybe if you are curious, what is the high frequency portion? What is the low frequency portion of the digital signal? See, this is the low frequency one, right? A flat portion of the signal, that is DC. And where are the high frequency one? The jumps. Oh, the corners, see? We have high frequency components of the signal. So the high frequency one will be filtered. And what you will get? Something like this. Okay? The higher frequency, the worse signal you will get at the receiver side. This is the transmitter side, that is the receiver side. So from the transmitter, you transmit something like this, perfect digital signal. But at the receiver side, if the frequency is too high, you will get something like this. Then tell me, what is the content of your digital communication? Nothing. You can tell. Okay? So, what we can help the digital guys. For them, nowadays, we hope we can transmit digital signal up to gigahertz. I warn you, I tell you, nothing is possible for such kind of direct communication up to gigahertz. Sorry for that. For our industry, the best for parallel digital communication in the past, we have only those two. 33 megahertz or 66 megahertz for our IDE. Yeah, that is some kind of interface for hard disk. That is already the best for humankind's industry in the past. Okay? For the so-called parallel digital communication. 33 megahertz is the maximum. But how to double it? We need to have shield. Okay? We need shielding between the digital lines. We need to have some shielding line. Okay? Yeah, usually we need to connect. We call it grounded, but you need to be very careful. Grounded doesn't mean you need to connect the wire to 0 volt. No. Okay? Grounded JD is some kind of AC idea. So only if the AC voltage is 0, then it will be good. So it only means that you connect all those shielding lines to fixed DC voltage. It will be good enough. Please keep this in mind. Okay? Especially in analog design, if you see something grounded, don't think it is connected to 0 volt. No, to some fixed DC voltage. Good enough. Okay. Yeah, that is really troublesome because the number of wells needs to be doubled to make it from 33 to 66 megahertz. Nothing is free. You need to pay more money for that. And after 66 megahertz, nothing existed in our industry. If you would like to speed up the communication, sorry for that, you need to change your mind from parallel to serial communication. 你就不能再做并列通讯，你要做串列通讯。Only for serial communication, you can achieve something far above gigahertz. But how to transmit such kind of 1 and 0? Up to gigahertz. Who can design such kind of transmitter or receiver? Analog IC designer. For such kind of high frequency, high speed, serial communication link, nobody in digital domain can design it. All right? And usually, we need to embed our clock into our data. Okay? 你需要把你的脉冲丢进according to the so-called clock skew. Right? Maybe. You're there? Oh, okay, anyway. What does it mean? For clock skew? Oh, you have many kind of, that is for parallel digital communication. You have a lot of data, a lot of I/O control bits, anything, okay? In the past, everything is synchronized by your clock, by your reference clock, all right? So maybe right now we have 64 bits or even 128 bits for such kind of parallel communication. I don't care. For 64, so you have D0 all the way to D63, right? So what is the problem for clock skew? Oh, again, nothing is perfect, even for the communication lines. They have parasitics, they are lossy. So the delay from here to there for each line is not the same. Sorry for that. So at the transmitter side, everything is synchronized to the clock, but at the receiver side, sorry for that. Somebody arrived earlier, somebody arrived later, right? That is a so-called clock skew, 时脉歪斜. So what you can do? Just in the class, especially in elementary school, we have the leader in the class. For each class, the leader will say, stand up, both, sit down, right? He needs to pay attention to all the classmates. Stand up. Then he needs to wait for the latest, for the slowest. Then you say, bow. Right? Look at the slowest one, then sit down. So it means what? The more clock skew, the slower operation you can achieve for such kind of parallel communication. That is one major issue why nowadays almost for nothing in parallel for high-speed communication. Everything is in serial. But why? The secret is we need to embed the clock into the data. So never mind what kind of skew, what kind of jitter. The clock is embedded into the data, so yeah, they follow each other Okay? By nature, they are synchronized. No clock skew. 他们已经牵进去了，一起晃，一起摇，一起 delay， 所以不会有时脉歪斜，自然而然的同步。That's it. But how to achieve such kind of? If you embed your clock into your data, that is from the transmitter side. So after you receive, the data and the clock are mixed. Oh, how can you extract your clock out to sample your data? We need help from phase lock, from lock loops, either PLL phase lock loop or DLL delay lock loop. Oh, so that is another hint. The top two analog IP actually is lock loop. All right. So if you can do very good data converter design or lock loop design, no worries. You can live happily since after. Okay. All the IC design houses, they need such kind of talented guy to help them design data converter, lock loop, blah, blah, blah. Top one and top two, good enough. Okay, allow me to speed up the explanation. Let's go back to the future. 我们回到未来，回到过去。Okay, let's have a look at such kind of problem. The low C cable. How can you speed up such kind of digital communication? That is one way out. We would like to transmit 2 bits or multiple bits instead of only 1 bit. Okay, from the beginning, you have only 1 here, 0 there, 1, 1, 0, 1, 0, 0, right? For each clock, we transmit only 1 bit. But here, a very good example. For each clock, we transmit 2 bits. Got it? You can see. If you transmit, so we call it how many, we call it baud rate. That is a very important idea in communication, in telecommunication. Okay? From the beginning, we call it bit rate, bit per second. Right? How about here? We call it symbols per second. We transmit symbols. And each symbol here means 2 bits. Okay? That is the most important idea to speed up the communication. All right? So baud rate is not equal to bit per second. No. Better than that. It depends on how many bits for each symbol you transmit. Okay? So it means what? The more bits in each symbol, the better communication speed. Wow. But why? Okay, let's have a look at the detail. If the clock is still the same, but we transmit 2 bits at the same time for each symbol. So 2 bits, 1, 0 here, then 1, 1, 0, 1, 0, 0. Right now we have 2 bits. It means what? 4 levels. In the past, we have only 1 bit, so you have only 2 levels, 1 and 0. But right now, we have 0, 0, 1, 1. So in between, we have 0, 1, 1, 0. Okay? So the result becomes this. But why it is better than the original waveform? Again, low C cable look like low pass filter. It loves such kind of DC, right? It hates such kind of jumps. You can see for DC level, the duration is doubled from the beginning. We like it. It enhanced the DC level for a longer time, right? And how about the jumps? Here and there. In the past, it needs to be from the bottom to the top, or from the top to the bottom. The transition is full range. But right now, we divide it into 4 levels. So on average, the transition is 50% off. Right? We double the DC component, we halve the AC component. DC 成分乘以2倍 ，AC 成分降2倍。Congratulations. After such kind of transmission, you will get much better waveform at the receiver side. Got it? Got it? So, how can you enhance it, improve it? You say, hey, I know the secret already. So for each symbol, I would like to transmit 3 bits, 4 bits. Congratulations, you get the point. But again, nothing is free. You need to pay for what? In the past, you have only 1 0. So everybody in digital domain, they know how to extract the content at the receiver side. Okay? Only if the waveform is good enough. If it is close to VCC, then they will think that is 1. If it is close to 0, they will think, oh, that is 0. Okay. In between, actually, for digital guys, above 50%, it is 1. Below 50%, that is 0. Oh, they live happily since after. They love it. We hate it. But right now, you need to be very careful. You have 4 levels. Okay? So if your input signal is here, how much is the content? How can you know that? By your eyes? No. By your circuit. By your analog circuit instead of digital circuit. We need the help of what? ADC. You need to make decision. If you have 3 bits, oh, sorry for that. 1, 2, 3, 4, 5, 6, 7, 8. Oh, and here, what is the content? There, what is the content? We need the help of ADC. Okay? At receiver side. And how about transmitter side? You need the help of DAC to convert the digital content into different analog levels. Okay? Got it? Hopefully, I help you as much as possible. The other very important idea for you is for such kind of digital communication means what? Everything in digital? No, sorry for that. Actually, nowadays, digital communication only means that the content is digital. Here, 1 0. There, 1 1. The content is digital. But the signal itself is analog. Got it? If the signal is digital, sorry for that. In digital domain, again, we have only 0 and 1. But right now, we have different levels. So, the signal itself is analog. Only the content is digital. Got it? All right? For our mobile phone, we call it digital mobile phone since the 2nd generation. How about the wave? The RF wave, you transmit all the audio, video, any kind of content is in digital. But how about the RF wave? Sorry for that. It should be in analog. Okay? So don't shade me. You say, hey, look, that is some kind of digital communication, so we can design it all those in digital domain. Sorry for that. For real transmission, it should be in the analog. So even for digital communication, they need a lot of help from analog IC designers. Actually, that is the bottleneck. For example, iPhone, Apple, right? Apple design its own code. Right now, A13, next A14, blah, blah, blah. I don't care. I don't mind. For all those, Apple can design itself. But how about the modem? The RF transmitter and receiver? Apple cannot. Okay? The best actually on earth is Qualcomm. And Apple should call Qualcomm for any kind of violation, blah, blah, blah. Okay? And after that, but Qualcomm stopped to ship the modern chips to Apple. How can Apple survive? It needs to buy chips from Intel. Oh, sorry for that. The performance of Intel modem is much poorer than Qualcomm. Then Apple tend to say to MediaTek, oh, the same. Yeah, worse than Qualcomm. So Apple was forced to negotiate with Qualcomm to get its chip again. Okay? RF modem, most in analog domain. Okay? Yeah, the modem is for such kind of iPhone, smartphone. It should be in digital. No. Again, I need to highlight that only the content is digital. Okay? The signal itself, the interface itself should be in analog. So, which one is the more or most difficult to design? Analog instead of digital. Okay? That is usually the bottleneck for such kind of high-end consumer product design. All right? So we need more and more analog IC designers to achieve it. Even in Intel, it designs CPU, MPU, blah, 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 the best CPU company on earth. It hired more than 50% of the engineers to do analog design instead of digital design. All right? Even in the past, for hard disk, we would like to store digital information on the surface of the disk, magnetic disk. Okay? 磁盘. The waveform look like this. The magnitude is only 2 millivolts. Tell digital guys to read the content. No, they will shake their head. Oh, we can't. We are not able to do such kind of dirty jobs. So who need to finish it? Analog IC designers. For wireless receivers, again, totally in analog domain. No digital guys can design anything like this. To transmit 0 and 1 directly to the air? No, it violates the regulation. Okay? In Taiwan, we have NCC, right? And in America, we have FCC or something. Anyway, don't transmit any digital signal into the air. This is too dangerous because for such kind of digital wave or square wave, you have harmonics. So if you transmit this at 1 gigahertz, it means what? The harmonics, 2 giga, 3 giga, 4 giga, everything is in the air. You have a lot of interference to the other base station. That is really harmful. Yeah. Our officers and the other company will kill you because you have a lot of pollution to the RF spectrum. 你污染了整个 RF 的频谱，你会吓死人。Okay? Again, nothing in the air should be in digital. No, sorry for that. It should be in analog. You cannot transmit such kind of square wave into the air. No. The only allowable signal is sine wave. Okay, you need to transmit sine wave, analog, such kind of analog wave into the air to make sure if you transmit at 1 gigahertz, only, I cannot say it is only 1 gigahertz. No, not something like this. A 9, no. A 9 means what? You transmit pure sine wave, 1 gigahertz sine wave to the air. For what? No information, no content. Humankind don't do any kind of silly things like this. Okay? We need to embed digital content inside such kind of sine wave. But how? For example, we have BPSK. Okay? That is very easy. By phase or binary phase shift keying. Okay? So you may say, this is for one. And the other one, the phase is 180 degrees indifference. That is for BPSK. One is in phase, the other one is out of phase. Something like this. Okay? So the signal itself is still sine wave, pure analog, but how to carry the digital information? With different phases. Got it? So how about the spectrum? Because you have 0 degrees or 180 degrees, so the night spectrum will be melted. 会被融化掉, huh? Just like this. So with the so-called bandwidth, it is tightly regulated by our NCC. How much bandwidth you can have for each base station, it is tightly regulated. Okay, not only for BPSK, if you have QPSK, it means what? Quadruple. 1/4. 0, 90, 180, 270 degrees configurations. You embed the digital content into such kind of analog signal. That is the so-called digital communication. Okay? Again, no digital IC designer can achieve anything for nowadays digital communication. Sorry for that. All of them should be designed by us. I mean, analog IC designers. All right? And I told you already, our life is harder than digital ones because we need to do a lot of trade-offs. Yeah, we need to pay attention to noise, frequency of operation, interference, power dissipation, money, the cost, blah, 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 blah. All right? And much more important is this, sensors. For each smartphone, we have more than 10 or even 20 sensors. Okay, so what is the definition for sensors? You need to convert signal from one domain to the other domain. I don't care from which domain to which domain. Okay? For example, the so-called ADC is one of the sensors to convert usually voltage into digital domain. From voltage domain to digital domain, congratulations, it is one of the most popular sensors. Anyway, nowadays, when we call something sensor, usually we are not talking about ADC. Yeah, we would like to convert some physical signal instead of voltage. For example, temperature sensor. What does it mean? To convert temperature into what? As you like. You can convert temperature into voltage. That is some kind of sensor. Okay? But it's not good enough. Our chip don't read voltage signal. In the baseband, they can only process digital information, right? So you need the help of ADC to convert the voltage into digital. Wow, that is too troublesome. Why don't you convert your temperature directly to digital output? Then we call it smart temperature sensor. Okay, so the definition for smart or not means you convert one kind of signal into digital output directly, into digital domain directly. Then the sensor is smart. Okay, but we have a lot of sensors, not only temperature sensor. Again, for example, we have proximity sensor. If you talk to the phone, right, far away, then the screen will be turned on. But if you make your iPhone closer to your face, then the screen needs to be turned off. How does it know that? Proximity sensor around here. Okay, 进阶感测器. Okay? Yeah. And we need accelerometer, 加速器, G sensor, a lot of them. Wow, fantastic. And, here, we need a lot of accelerometers in the cars, smart cars. For what? To control airbags. All right? So if something wrong, you drive your car, to hit something or hit somebody or hit another car. You have any kind of car accident, serious car accident, then the sensor Just like accelerometer need to issue some warning signal for the control system to pop up the airbags to protect the users inside, the riders inside. Okay? So from the very beginning, tell me, how can you sense such kind of acceleration, 加速? How can you sense that? Oh, the idea is quite simple here. That is the first generation for accelerometer in the cars. It has only 2 plates. This is a fixed plate. It means it cannot be bended. All right? And the other one is deflectable flat. It can be bended according to your acceleration. So you see, if your car is accelerated in that direction, then the deflectable plate will be bended backward. That's it. So it means what? The capacitance between those 2 plates, one is fixed, the other one is deflectable. The distance will become smaller, right? So it means what? The capacitance will be increased. Oh, it means the car is accelerated to the right. On the contrary, if it is accelerated to the left, then the fixed is already fixed. So the deflectable will become that. So it means what? The gap becomes larger, the capacitance becomes smaller. So in the past, you only need to know the absolute value of C1 becomes larger or smaller. Then you will know the acceleration is to the right or to the left, to the front or to the back. That's it. Right? Wow. If you are the first one to create such kind of crazy idea, piece of cake. Oh, yeah. Only if you know something about fundamental physics, you can think about such kind of very simple idea to be applied here. Okay, if you are the first to think about it, you can apply the patent. All the car company needs to pay you a lot of money. But sadly enough, the first generation patent killed a lot of people, especially killed a lot of rich people. Why? Because for absolute value, the life and death is between 1%. Wow. 1% of diffraction here or there, you need to decide whether or not to pop up the airbag. That is too dangerous, right? Why a lot of rich people were killed? Only rich people in the past had money to buy such kind of luxury car, with airbags. For poor people, they don't have airbag, so they need to watch very carefully. But for rich guys, they can speed up. Wow. They are really happy on the highway without speed limit. But if the road is a little bit bumpy, some kind of holes on the highway, or some stones are high, small stones, good enough to kill them. Why? Because after the car ran over the stone, right, such kind of vibration will make the flat vibrate in this way. Then, nothing wrong. The car didn't hit any kind of the mountain or the other car. No, only bumping, right? But 1% means too sensitive. Then the airbag will pop out. And the rich guy couldn't see anything in front of the car because the airbag is too huge, too big, right? So many of the rich guys passed away. They sued the car company a lot. So what is the solution? Oh, this is the second generation. You can see it has 2 fixed plates and only 1 deflectable plate. That's it. But it says what? Again, the difference between C1 and C2. Here, we sense the absolute value of the capacitance. There, we only sense the capacitance difference. So it means what? Here, for the difference, we sense positive, negative 100%. Got it? And there, positive, negative 1%. Here, the scale is increased by 2 orders. Okay, so it means, it is much easier for you to make the decision whether or not to pop out the airbags in a much, much safety way. Okay? That's it. For patents, actually, this is much safer. Okay, much, much safer than that. However, if somebody claims such kind of patent already and you created another one, you still violate the original one because you have everything the others had. Here, here, there, there. You had one extra one. You have extra one different from the original, right? And it is functional. It has some kind of functionality. That's it. You can apply the new patent. We call it subordinate patent, 下位专利. Okay? But you have all those components of the previous patent. So you still violate their patent. So this is the superordinate patent. You violate their patent, but yeah, they will sue you. Hey, don't use my patent, okay? So both go to the court to argue how much you need to pay. They will say, oh, you need to pay me $100 each. They say, oh, I will only pay you $1. And how about the result? Usually, the judges will, how can I say? Yeah, will get much more benefits for the subordinate patent. Maybe the judge will say, oh, okay, you only need to pay $2 or $5. Good enough. Okay, here and there, their wish and your wish in between, the final will be much closer to the subordinate patent. All right? That's it. So, what is the best way to fight back? Because for international companies just like Qualcomm, Apple, Samsung, they have a lot of patents. Even TSMC, they have a lot of patents. The best way to fight with them is to create something called subordinate patent. Yeah, you violate theirs, but you add some more components to enhance the performance. Okay? If the performance, if the functionality is not enhanced, you apply some extra component without any kind of performance improvement. Sorry for that. Yeah, you cannot get any kind of patent. Got it? Got it? So for a cup, see, that is another good idea. A bottle or a cup. Somebody file some patent like this, then you'll say, hey, oh, okay. I need to have one patent here. For what? You can carry the bottle or the cup easily. That's it. You have extra components to enhance the performance. Right? You got another patent, but it still violates the original. Because if you have all those components they have, okay? One more. And then the other guy says, oh, I have 2 more. You can say, hey, I can carry this by 2 hands. Yeah, you get more stability. Got it? Yeah, you get another subordinate patent. Right? Oh, I see. So here, there, for what? No. Yeah. You need to explain what kind of performance you can enhance by such kind of outcome. Otherwise, you cannot get any subordinate. Okay? Anyway, anyhow, even for microcontrollers, microprocessors, memories, I think most of you will think, oh, they are digital chips. Yes, yes. But inside the chip, on the chip, like nowadays we have a lot of high-speed I/O circuit, right? Who designed such kind of high-speed I/O circuit? Sorry for that. We, instead of them, I mean analog IC designer, instead of digital IC designer. Okay? For any kind of high-speed transmitter receiver, anyway, okay, it should be analog design. Okay? Yeah. Even in memory, DRAM, we have sense amplifiers. Who designed it? Analog IC designer. Okay? Briefly, what are you required to be a good analog IC designer? Yeah, I emphasize very much in analog domain. Yeah. From the very beginning, you need to be very good at microelectronics. Why? Because almost all the circuits in analog IC design evolves from microelectronics. OK？ 对比 IC 设计里面，几乎所有的电路都是从微电子学过来的。So, if you have time, please go back to refresh your own mind. For microelectronics, it is very, very important for analog IC designer. That is the most fundamental. Okay, so if the students go to, any student goes to my office and he or she would like to join me, I always ask them to show me the transcript. And then I will focus how much grading they got for their microelectronics. That is from the very beginning. And then I will have a brief look for the overall GPA, good or not. Okay, yeah. Anyway, after that, if you are very good at microelectronics, congratulations, you get the ticket to join us. And what? You say, oh, piece of cake. Most of the students, they are very good at microelectronics. I mean, in this class, right? So how can you survive? No, how can you be outstanding, be more outstanding than the others? Hardworking. Okay? Just like this, as you sow, so shall you reap. 要怎么收获就怎么栽。Okay. Anyway, hardworking means the most. Yeah. But you say, hey, I'm smarter than the others, right? Sorry for that. IQ is not everything. No, sorry for that. EQ is much more important. EQ means what? Hardworking and then innovation. That's it. You need to be innovative to create something new, just like this. See? You can apply the patent. Your company will make a lot of money, but you are the inventor, right? You can share some of the profit, some of the bonus. Yeah, your company makes a lot of money, you too. Got it? Oh, sorry. I changed my mind to replace the story. Okay, that is another joke. Allow me to show you one of. I told you in last week. This is one of my students. He studied in such kind of Oriental Institute of Technology, 东技术学院. Anyway, where is OIT? I have no idea because that is not so good. Oh, sorry for that. Yeah, I cannot tell you the truth. Okay. So, maybe this is wrong. Sorry. 4 years that to get his bachelor degree. Then 2 years here to get his master's degree. And after 15 years of hard working, he became the R&D head for Sitronics. Sitronics actually, it has a few daughter companies. One of them maybe called Jiasheng. I have no idea what's in English. That is for sensor. Okay, for sensor design. And the stock price for the mother is around 150. And for the daughter is around, more than that. All right? Sensors means a lot of difference. Okay? For Sitronics, actually, the major business, I think, something like LCD driver, OLED driver, or something like that. Okay? LCD, LED, OLED, I mean. Yeah, mini LED, blah, blah, blah. That is for the mother company and the daughter company. One of the daughter companies design chips for sensors. Yeah, it makes a lot of money. Each year, the EPS, it says that maybe about 30-something to 40-something. Okay? So it means you invest $1 each year, it can help you to get $3 or $4 back. Oh, it is much better to rob the banks, right? If you rob the banks, you get money for free, but you need to pay for it. If you were caught, then put in the jail for your whole life. So it is much, much better than robbing banks. 这个比抢银行较好谈。Yeah, the other, we can have a brief break here, but before our break, yeah, the other 2 jokes for you. I do my very best to wake you up or to inspire you. Yeah, that is the truth. Oh, here is a very good story for you. Yeah, but in Chinese. I have no time to translate into English, but in brief, Toshiba in the past competed with Sony very much. For what? For domestic electronics, home electronics. One of the example is electric fans. Just like over there, Sony was the top one. Toshiba fabricated a lot of e-fans, but the market share is really small. Never mind how hard they do. They have a lot of commercial aids, a lot of promotion, but the market share was really, really low. And the company has a serious problem. Maybe it would go bankruptcy if it couldn't sort out the e-fans. The owner, or maybe the president of the company, in one morning, he told all his employees, anybody, please, somebody do something. If you can help our company to sell all the e-fans, then you will get 10% of our stocks, or 10% of stock share. All right? And everybody tried his or her own very best to create any kind of crazy idea, blah, blah, blah. But one of them said, hey, look, if you go to the market, Sony only sells black e-fans. And we also produce such kind of black e-fans. It's ridiculous. Why couldn't we change the color for the e-fan to be red, to be white, to be green, anything else than black? Oh, good idea, right? So after that, they recolor the e-fans and sold all the e-fans out. The company made a lot of money. And the guy get 10% stock. Wow. That is the so-called innovation. You need such kind of innovation to be talented, to be outstanding in this field. IQ, again, means, I cannot say means nothing, but IQ is not everything. Just like my student, he defeated all the PhDs from NTU, NTHU, yeah, NCTU, NCKU, all of them. Okay? He only got master's degree from my lab. So again, I told you you have much more potential than your own imagination. Just try to squeeze yourself, to reach the upper limit of your capability. You can live happily since after. So the other joke is here. Once upon a time, there was a mother tiger. She gave birth to a lot of cubs. But after some days, all the cubs passed away. So the mother tiger had a very serious postpartum depression, 产后忧郁症. Okay, she wouldn't like to eat. So what we can do? Nothing, right? No worries. Some employee in the zoo has such kind of innovation. He tried to steal some of the piggies from the mother pig and put on tiger clothes. Wow, to make the mother tiger very, very happy. That's it, innovation. But my question is, after some weeks or some months, the baby, the piggies will become big pigs, right? Without the clothes. What's the reaction from the mother tiger? Oh, let's wait and see. Okay. So, pay attention to what you're required to be an outstanding analog IC designer. Hopefully, I cannot say all of you, most of you can achieve something instead of nothing in the future. Let's have a brief break here.